Hello class, today we're going to go over related rates again. And just like yesterday, I am going to go over specific examples that are very similar to the ones that you will be working on, just some different numbers. So let's start with the first one. A golfer hits a ball into a pond of still water, causing a circular ripple. If the radius of the circle increases at the constant rate of 0.5 meters per second, how fast is the area of the circle increasing when the radius of the ripple is 2 meters? So let's first start with defining our variables here. So we're dealing with area, so A will be area. We're dealing with a circle, so that will be R for our radius. And of course we have time. I don't know why I wrote time first, but time equals t. There we go. We will also have dA dt. That's going to be the rate of change of the area. And then we have dr dt. That's the rate of change of the radius. And we know that value to be 0.5. That's how quickly the radius is changing, 0.5 meters per second. And then let's see here. Okay, what are we looking for? How fast is the area of the circle increasing? So we're looking for dA dt. So we want to find dA dt when the radius is 2. When r is 2. Okay, so now let's think about what is the area of a circle. That's going to be A equals pi r squared. And so now we have we've defined our variables. We've come up with an equation that models a situation. So now we need to take the derivative of the equation. So we're going to have dA dt is equal to pi. Remember, pi constants, we don't need to take derivatives of constants. Pi times 2r, just using the power rule here for r. Oh, and then I forgot my dr dt. Awesome. And now that we've taken the derivative, let's just go ahead and plug in values. So we're looking for dA dt, so that's already solved for. So we have dA dt of pi times 2 times our r, which r is, we want to know we want to know the rate of change of the area when the radius is 2, so that's another 2 there, times the rate of change of the radius, which is 0.5. So we have dA dt, doing all that math. 2 times 2 is 4, times 0.5 is 2. So we're going to have, so the rate of change of the area is 2 pi meters per second. All right, let's take a look at a balloon problem. So a spherical balloon is inflated at a rate of 10 cubic meters per minute. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So now we're dealing with surface area. We want to know how quickly is the surface area increasing. So we're not dealing with volume here. But we do need volume in there because this is a volume. It's being inflated by 10 cubic meters per minute. That's a volume. So we will need volume, but we're not solving for volume. So let's start with S is going to be our surface area. V is going to be our volume. R is our radius, because we are dealing with a sphere, and T is time. Of course we need time. So let's see here. We're given a dV dt value. So that's going to be the rate of change of volume, and that is given as 10 cubic meters per minute. 10 cubic meters per minute. We will also have, let's see, Well, we're looking for ds dt, the rate of change of the surface area, and we'll also run into dr dt, the rate of change of the radius. And what we're finding is ds dt. So find ds dt when the radius is 3, when r is 3. Okay. So this is an interesting example. Here we're actually going to have two functions, and the reason why is because we need to be able to tie together all of these variables. So the volume has a radius in it. The surface area, or the formula for the volume, has a radius in it. The formula for the surface area has a radius in it, but the surface area and volume aren't connected, but we need those connected as well. So I'm going to start off with the volume of the surface area, the formula for the surface area. Well, no, I'll start with the volume first. So volume is 4 over 3 pi r cubed, and then the surface area of a sphere is 4 pi r squared. There we go. So how about let's take the derivative of both of these. This is our first time working with two functions. So let's take the derivative of both of these. So this left function will be dv dt is equal to, well, 4/3 pi. That's a, those are constants. So we're going to have 4 over 3 pi. And then we need to take the derivative of r cubed. That's going to be 3r squared dr dt. And let's take the derivative of this one. So this is going to be ds dt of 4 pi is constants, times 2r dr dt. Okay. So now we want to, well, actually, let's clean these up a little bit. Notice that here this 3 will cancel with this 3. So we can have dv over dt, or dv dt, is equal to 4 pi r squared dr dt. And the second one is, we can multiply these, the 4 and the 2 together, to get ds dt is equal to 8 pi r dr dt. Okay. So these are our two functions. Now, we want to be able to relate them to each other. So what I'm going to do is I'm going to take one of the functions and I'm going to solve for dr dt, since they both have dr dt in it. So I'm going to take the left one and solve for dr dt, which means we need to divide both sides by 4 pi r squared. So this is going to look a little ugly for a moment, but we're going to, so this cancels all that. So we have dr dt is equal to dv dt divided by 4 pi r squared. So now that I have this, I'm going to go ahead and plug this into dr dt right here. And I'm actually running out of room, kind of. But let's see here. So I can say ds dt is equal to 8 pi r, and then dr dt is going to be the dv dt over 4 pi r squared. And you can see a lot of this stuff will cancel out for us, so that's kind of nice. Let's go ahead and clean this up. So we have ds dt is equal to, let's see, 8 divided by 4 is 2. These pi's cancel, and this r cancels out the square. So we have 2 2 over r, really, times dv dt. Boy. Okay, now we can plug in our stuff. Okay, so we created our two functions that included all of these variables in them, and then we solved one of the functions because we need to relate these two functions. So we solved one of them, plugged it in for something, plugged it into the other thing, or into the other function, and we got ds dt equals 2 over r dv dt. And now we can just plug everything in. So ds dt is equal to 2 over r. Well, r we want it to be 3. We want to know the rate of change of the surface area when the rate is 3. So 2 over 3 times 10 r dv dt. So this is going to be equal to 20 over 3. And our units, this is surface area. So let's see, what would our units be here? Let's see. This is always the bane of my existence is getting units. Oh, surface area. So meters squared per minute. Okay. Awesome. Let's see here. Okay, let's move on to the next example. A rectangular swimming pool, 10 meters long and 5 meters wide, has a depth of 3 meters at one end and 1 meter at the other end. If water is pumped into the pool at a rate of 0.3 cubic meters per minute, at what rate is the water level rising when it is 1.5 meters deep at the deep end? So let's draw a picture here. I'm going to do a side view of it. So let's see, we have a pool that, let's see, it's 10 meters long, and one side goes down 1 meter, and the other side goes down 3 meters. And so it kind of looks like this, and we're going to have water in here. And yeah, okay. So the water is filling up the pool, and we want to know at what rate is the water level rising when it's 1.5 meters deep. So what is the h? So let's, well, yeah, h. We need h here, and this would be the length of our water. So let's define our variables. Well, we are dealing with cubic meters, so that's going to be volume. Then we have height. We have length. We'll also have a width. It says the width it's 5 meters wide, so we're going to have a width as well. And we're also going to have time, of course. Okay, so now let's kind of define our, or let's define our rate of changes. We're going to have dV, the volume is changing. That's the rate of change of volume. And that is given as 0.3 cubic meters per minute. And then we're also going to have the rate of change of the length, because the length is going to change too, right? So we're probably going to run into that. And then we're going to have the rate of change of the height, and in fact, that's what we're looking for. Notice we won't have a w, or we won't have a dw dt because the width isn't going to be changing of the water. The width will be remaining the same. So what are we looking for? We want to find. We're looking for the dh dt. when the height is 1.5. Okay. So now let's start going through this problem. Now we need a we need a formula. Let's see, what is the shape of the pool? Well, the pool water, we're just concerned about the water portion. So this is a triangle here. So we can say the volume, let's see, what's the volume? Well, what's the area of a triangle first? It's going to be 1/2 times h times L, right? H times L, 1/2 of that, times the width. That's going to give us the 3D shape. Okay. So we have, that's a weird looking W. Okay, whatever. So we have 1/2 times height times length times width. And we are given the width, right? The width is 5. That's not going to change, so we don't need that as a variable. So we have volume is equal to 1/2 HL times 5. And we can just kind of clean this up. So V is equal to 5/2, or 5/2 HL. Okay, so now what we want to do is, notice we're not given a length of, we're given a specific height, right? So that's good, but we're not given a specific length, and we need to find that out. So what we're going to do is we're going to use similar triangles. So notice I have this small triangle here, and this might be bringing us back a little bit. And then I have this larger triangle right here, and they're similar triangles. So let's create a similarity statement, shall we? Remember making similarity statements? We could say like one side is to another side as one side is to the other, but they need to be related, right? So I can say L is to H. So the length of my small triangle divided by the height of my small triangle is equal to the length of my big triangle divided by the height of my big triangle, which is, well, this is going to be 2 actually. Not 3, because 3 is all the way to the top, but we need to subtract this 1 from it, so it's just going to be 2. Awesome. Now let's solve for L. Okay? Because what we want to do is we want to get rid of the L. We're not given an L. We want it all in terms of height if we can. In this case, we can. That's why we made this similarity statement. So we're going to cross multiply here. So 2L is equal to 10H. And then we're going to divide by 2. So L is equal to 5H. So I'm going to go ahead and substitute that in for L so we can have it all in terms of H, because we're given an H value. So V is equal to, let's see, 5 times 2, H times 5H. And if we're to clean this up a little bit, we're going to have the volume is equal to, let's see, 5 times 5 is going to be 25/2 H squared. And now we can take the derivative of this thing, now that we have it all nice and good for us. So, to take the derivative, let's see, we should be getting pretty good at this by now. dv dt is equal to 25/2 times 2h dh dt. Right, h squared turned into 2h from the power rule. Okay, so we can clean this up a little bit. These 2's cancel. So we're left with dv dt is equal to 25h dh dt. Okay, now we've derived our function and simplified it. So let's plug in our values now. So we're looking for dv of t, or dv dt. That's what. Oh no, we're looking for dh dt, and we're given dv dt. So let's plug it in. So 0.3 is our dv dt. So 0.3 equals 25 times h, which the h is the 1.5, dh dt. Okay, wow, I'm running out of room here. I'm going to go back up here. Okay. So now what I want to do is I want to get dh dt by itself, so let's divide both sides by 25 times, well, what is this? Let's just rewrite it. 0.3 equals, this would be 37.5 dh dt. And we want to divide both sides by 37.5. And let's see, let me get my calculator out if I can find it. Ah, there it is. It's hiding in my math book. Okay. So let's see. 0.3 divided by 37.5. That's 0.008. So our dh dt is equal to 0.008. And the units, let's see, it's the height, it's a single, it's not an area, so it's not squared or cubed, it's not a volume, so it's just going to be meters per minute. So it's rising at that rate, 0.008 meters per minute. Okay, so on to the next one. So a person standing at the end of a pier is docking a boat by pulling a rope at the rate of 2 meters per second. The end of the rope is 3 meters above water level. How fast is the boat approaching the base of the pier when 5 meters of rope are left to pull in? Assume the rope never sags and that the rope is attached to the boat at water level. So let's draw a nice little picture here. So here's the water. We have a boat. That's a sad sail, but okay, we have a boat, and we have a pier, or a dock of some sort. And there's someone up there, and let's see, I'm going to draw an orange. So we have a rope, he's pulling a rope. Threw that a little too high for the guy, but oh well, we get the idea. So we have something like this, and this is the rope here. So, what else do we know? Oh, the rope is 3 meters above water level, so that's 3. Okay. So what are we looking for? We're looking for how fast is the boat approaching the dock. So we're going to call this one X, and let's call the length of rope L. So let's define these. So we have, so L is the length of rope. X is the distance from dock. And then dLdt, let's see, so we will have a dLdt because the length of the rope is changing, right? And in fact, we're given our dLdt. It's being pulled in by 2 meters per second. So it's the rate of change of rope length. And that's given as 2 meters per second. Okay. And then we have dx dt, which is the rate of change of distance of boat from dock. And that's actually what we're looking for. So we want to find dx dt when L is, there's 5 meters of rope left. Okay. So let's set this up. So we're dealing with a right triangle here, which just screams Pythagorean theorem. So let's go ahead and set that up and see what we can do. That would relate our x to our L just perfectly. So we have 3 squared plus x squared is equal to L squared. Cool. Now let's take the derivative. So 3 squared, that's just a constant term, so that's going to go away. We're going to have 2x dx dt. equals 2L dl dt. And let's see, we're solving for dx dt. So let's divide both sides by 2x to get dx dt by itself. These 2's cancel. This whole thing cancels. So we have dx dt is equal to L over x dl dt. And you might notice something interesting here. I believe this happened on one of the questions from yesterday too. We are given an L length, right? When L is 5, we can go ahead plug that in, and we have a dl dt, that's 2, so we can plug that in. But we don't have an x value. However, we can find out our x value. So check this out. We have a right triangle here. And we know that this side is, I'll stick with the orange, so this side is 3. And we know that we want to find out the x length when L is 5. So L is 5. And, well, there you have it. If you're good with Pythagorean triples, we know that this is a 4. Right? 3, 4, 5 triangle. Or you could just solve for it if you'd like, using Pythagorean's theorem. So x is 4. So our dx dt is equal to L over x, and L is 5 and x is 4, times dx dt, and that's given us 2. Oh no, sorry, times dl dt, and that's given us 2. So, actually, one arrow. Dx dt is equal to 10 over 4, which is the same as 5 over 2. And we're dealing with length, so it's going to be meters per second. Awesome, so 2.5 meters per second. The boat is getting closer to the dock. All right, got one more for us. This one's an interesting one. A revolving light located 5 kilometers from a straight shoreline turns at a constant angular speed of 3 radians per minute. With what speed is the spot of light moving along the shore when the beam makes an angle of 60 degrees with the shoreline? So, okay, let's start by drawing a picture. So let's see, we have a shoreline here. We have the lighthouse, and let's see, it says 60 degrees with the shoreline. So we want to know 60 degrees right there. This is a right angle. And I'm just going to label these. This might come in handy. Well, actually, it will come in handy. B and C. And we know the distance from the lighthouse to the shore. Oh, this is the shore, by the way, up here. We know the distance to the lighthouse to the shore is 5. And we're going to call this angle just theta. Remember, theta is a variable that we use when referring to angles. So, boy. Oh, what else? We probably need something else. Let's see. With what speed? Okay, so we need to. Okay, so with what speed is the spot of light moving along the shore? So let's call this x, and that means we'll be looking for dx dt. Because think the lighthouse. So if you're unaware, lighthouses, they're big towers with lights, and they spin like this. Their lights go like that. So we want to know what is this? At what speed on the shore is the light moving? Okay. So let's start with defining our variables here. This one's a tough one. X equals let's see, the distance. So because the light starts at B, I'm going to label the x value as the distance from light beam to point B. We're going to assume this thing turns clockwise. Okay, and then we have theta. So that is the angle the light makes with the line AB. right? Yeah, AB is this line right here. Okay, and then we have time, of course. And let's see. So we're going to have dx dt, and we're going to have d theta dt. And dx dt is going to be the rate of change of the light of light. And then d theta dt, let's see, that's going to be the angular speed of the light. How quickly it's actually turning, right? And I believe we're actually given that value. We're given the constant angular speed of 3 radians per minute. So that's equals 3 radians per minute. Okay. Now, what are we looking for? We want to find dx dt. When, let's see, we want to find dx dt when theta is 60 degrees. I just realized we're going to come into a problem here, because this is in where are we? This is in radians. This is in degrees. So let's actually go ahead and just switch the 60 degrees to radians right now. No, we'll do it later. Okay. So now we need to come up with an equation that connects my theta and my x, my two variables here. And that's going to be a trig function, right? When we're dealing with side lengths and an angle, we're going to deal with trig functions, sine, cosine, tangent. And if you recall which one deals with opposite and adjacent, that's going to be tangent. So we can write the equation tan of theta is equal to x over 5. And then we can solve for x just to make it look a little nicer, get rid of that fraction. 5 tan of theta equals x. Okay, so now we want to take the derivative of our function. Let's see, so we're going to have, I'm going to switch these real quick just so x is on the left side. I just kind of like that better. So the derivative of x is going to be 1 dx dt, or just dx dt, equals 5 as a constant. And if you recall, we learned this, gosh, I believe it was before break. The derivative of tangent is secant squared theta. So remember, secant is just 1 over cosine. So secant squared theta, then we have d theta dt. Okay. I don't really like working with secant. I know it's 1 over cosine. So let's rewrite this thing. Dx dt is equal to, let's see, 5 over cosine squared theta d theta dt. You might be wondering how we went from here to here. Well, this 5, this is going to be it's going to remain on the numerator. Secant squared, let me just write this off in a different color here. Secant, well, I'm just going to say secant of theta is equal to 1 over cosine of theta. So that's why the cosine went on bottom, but since it's secant squared, it's cosine squared. Okay. All right. Now, let's see. So we derived, and then now let's plug in our values. So we're looking for dx dt, so this is what we're looking for. Equals 5 times cosine squared of theta. Now, what is theta? When this is 60 degrees, this is 30 degrees, right? Remember, the interior angles of a triangle must add up to 180 degrees. 90 plus 60 is 150 plus this 30. So this will be 30. However, as I mentioned earlier, it's in radians. So we're going to have to convert 30 degrees into radians, which is going to be pi over 6. All I did was just convert the degrees to radians. you can multiply. Here, I'll show you how. You can take 30, I'll do it in this color again, 30, and multiply it by pi over 180. So 30 pi divided by 180 is pi over 6, or 1 pi over 6. Okay. Times are, so going back to this, times are d theta dt, and we're given that as 3. And let's just, let's clean this up a little bit, simplify it. So dx dt is equal to 5 times 3 is 15 over cosine squared of pi 6. So let's see. Cosine of pi 6 and square it. 0.75. So let's see. That's going to be 20. So dx dt is 20 kilometers per minute. Boy, so that's how quickly the light is moving along the shore at that point. So that's all I have for y'all today. Let me know if you have questions and get started on the worksheet. Bye.